thank you so much, Dinar, for the warm welcome and introduction. So hello, everyone. Today I'm going to talk about eBPF and its usage in cloud security and how it is revolutionizing the concept of security dynamics in clouds. So I will start with a very basic introduction about what eBPF is. I'll also demonstrate few things around how you can use eBPF for doing some really fancy and cool stuff. And I'll also talk about the research that I am doing in this particular area. But before starting, I would like to again give you a short introduction about myself. So I am a security engineer by passion and profession with 8 years of experience, currently leading security team at Ethos. Ethos is a US insurance tech startup in India, so I'm from India. I have my area of interest personally lies in SSDLC, AppSec, and cloud security. I'm also a founder of Security Zines. If you're not aware of Security Zines, a very informative magazines based like for security. And I use very comical notation to like make security really simple for everyone, like across everyone. So yeah, Dinar already mentioned that I've worked on these companies. I started with Walmart, worked in Visa, Gojek, and Ethos. So my personal area of interest lies in building enterprise-grade solutions because I have some expertise around security as well as I have some idea of how to efficiently write scalable solutions. So that's what, when I wrote a really good scalable solution for GCP Cloud Infra, which is CureIM, you can check it out, it's an open source one. And yeah, I've spoken at multiple conferences in past. So that's pretty much about me. I'll go to the topic, the hot topic of today, which is eBPF and cloud security. So let's start with eBPF. What is before starting with eBPF, sorry, I would like to give you a very quick overview of what I'm going to cover in today's session. So I'll talk about what eBPF is and what makes it so special. And then I'll also talk about few things about eBPF which is verifiers and loaders. And also how this packet filtering still uses the same name, although it does more than packet filtering now. But we use still the same name. And I'll also talk about the dynamics of kernel and user probes, K probes and U probes, if you're aware of it. It's very much linked to very like kernel module code writing and stuff. And then I'll talk about the usage of eBPF in cloud security and at last few cloud security use cases. And I'll also talk about what future holds for eBPF and how does the future for eBPF looks like. So that's pretty much about it that I'm going to talk today. I'll also want you to, at the end, so that we can discuss about how your thoughts and eBPF can like add on to the cloud security topic and going ahead. So last few minutes I would like to keep for discussion around this particular space because this is very much close to my heart. Okay, so let's start with the eBPF. So eBPF stands actually for Extended Berkeley Packet Filters. So they were initially designed to filter out packets on the network level. So that's how they got their name, like packet filters. And they were written in user space that used to talk to kernel space. So you know that when you write a code in a Linux or Unix environment, there are two spaces, kernel and Unix. So you write your code in user space, and then you load it in kernel space, and then you govern few things around the kernel space itself. And in user space, when the eBPF program is loaded, it actually goes for the kernel module verification. So kernel has to verify. So if you remember in the previous slide, I talked about verifiers, right? So kernel has to verify this program is good enough to run inside the kernel module because you are giving user a flexibility to run inside kernel. And that's really, I would say, administrative job. So kernel has to verify certain things about it. I'll talk about it in the coming slide, but that's the overview. So kernel do some sort of verification of the module that user wants to load. And once everything's looked good, kernel said, yes, please go ahead. And once the module is loaded inside the kernel, so every execution of the code that happens, the kernel dumps the output of that to the eBPF output, I would say, location. So that could be anything. Console is one of them, but eBPF output location can be anything. Okay. So yeah, that's how the idea of eBPF came into picture. I'll also talk about how the initial code that was designed looked like, okay? So yeah. So this was the very first code that eBPF actually was referring to. So if you see that LDH and JEQ, L1 and L2. So the first example of eBPF that has come was when you wanted to monitor or filter out the packets at the kernel level, that if this packet belongs to the IP layer or Ethernet layer. That's it. That was the first, I would say, code that was written, and it was written in assembly language. So if you see the LDH, what it does, it loads the 12th byte of the packet, like the 2 bytes of the, I would say, of the packet at the 12th location to the register, and then it equates that if it is a Ethernet type or an IP type. If it's an Ethernet type, it goes to L1 and something like that. So the very first code of how eBPF looks like, and that's how it got its name, like packet filtering. But in the current scenario, eBPF actually can do anything that you can think of in user space and in kernel space. So we'll talk about it now. So in Linux or in any Unix flavor environment, there are 2 spaces, user and kernel, and user space talks to kernel space via system call interface. You can directly talk to kernel. There is a system call interface. There are a lot of system calls, and user space uses those system calls to talk to kernel. So that's the overall idea of this Linux as an operating system is. And that's where in these, if you see, there are 3 components, right? 1, user space, system call interface, and kernel. So eBPF can fit into any of these interfaces. And it's an event-driven architecture. So you take the eBPF module, you plug it out, put it inside user space, and then make it an event-driven architecture on the user space itself. So there was, this is very funny that I saw on internet. It talks about like how, let's say if you want to include any specific functionality inside a kernel in Linux in open source, then you have to wait for really, really long, because you have to get the approval from the community. Kernel is an open source, right? So you have to get the approval from the community, and that's the problem because it takes time. And by the time you have the approval and you merge your code into the kernel space, the requirement actually changes. So that was the whole problem that I think people, the maintainers of the kernel identified, and then that's why they gave this flexibility to user space so that they can write their own modules. But they did not want to give this flexibility as extension of kprobes and uprobes. Rather, they wanted to give it as a extension to the Berkeley Packet Filters. Okay, so yeah, let's come back to this diagram now. Now, as I talked in my previous diagram, that you can actually plug and play eBPF modules inside every user space application, inside every running kernel module, and inside every interface that exists between kernel and user or outside of it. So for example, if you see in this diagram, there are 2 interfaces that kernel is talking to. One is a storage interface and one is network interface. So you can actually plug eBPF on these locations. Now, the catch here is that if you see in the storage one side, the file descriptors and the block device modules of kernel, they can't allow you to write. Okay, so there are few limitations of eBPF, but yeah, so just for now. So there are few locations that you can't actually inject your eBPF filters on, and there are few locations where you can actually write anything on top of it. So I'll also talk about one of the research that I am doing, where I'm planning to integrate eBPF, cloud security, and AI to do checks on the runtime itself. Yeah, so something that we can see from this diagram is that the process that runs in network side can not just monitor things, but since it has a name that filtering can be done, it can actually block things. So for example, all of us know about WAF, right, or firewalls. So firewalls has this capability, or they could be hardware or software based. So they have the capability of filtering the packets. So you can actually do the same thing from eBPFs as well. I have a small demonstration to show how that can be done. But yeah, that can be done from the eBPF as well. Also, I forgot to mention that eBPF logo got, like there was a very amusing story that how this logo came into picture. So it's a B, and it's like eBPF. So that's how the logo came into this. And I'm not sure if it is visible or not, but there are extensions, as I mentioned, that there are extensions that you can inject your eBPF filter on these locations, but there are locations where you can't. Then you have to take the help of kprobes, which is kernel probes. And if there are locations where you can't put on the user space, then you take help from user probes. So kprobes and user probes are extension of kernel modules that helps you write code that can be injected onto user and kernel space, or you can actually get probes from that. So that's how the name kprobes came into picture. Okay. So now I want to talk about one thing, which is verifiers and loaders, because it is really, really important for us to know what makes eBPF so special. So eBPF is a non-intrusive way. It doesn't, like, it goes inside the kernel, but it doesn't affect your application at all. Like, it doesn't introduce any sort of latency to your application because it's very, very fast. And how it becomes very fast, I'll show in this diagram. And there is one thing that eBPF verifies, that the kernel should execute eBPF complete. The execution of eBPF should be completed. So this is something that kernel makes sure of, even before the eBPF program runs. So it does some sort of static analysis on top of your module. And if the static analysis workflow returns fine from kernel's perspective, then only the eBPF module is loaded inside your kernel space. So there are a lot of things that kernel does. It can't simply take your code and then run it inside your kernel. It doesn't happen. So it does a lot of things. So one thing is to ensure that the program who is loading eBPF has the privilege. Other thing is the program should not crash. One more thing is the program should complete. Program should have a flow that completes itself. It should not go into I would say runtime loop. Those kind of things, kernel do make sure of it by doing some sort of static analysis. And once that is done, we call eBPF program as approved. So this is just one part of it. So kernel approves this particular program to get loaded inside eBPF. Now, this translation, if you see, this is we'll see in the upcoming slide that this is a high-level program. You write your eBPF as a high-level code, but kernel doesn't. Like, any operating system has to translate that code to assembly language, and assembly language is interpreted. So you have JITs, like just-in-time compilers, to do the translation and interpret that. Okay, so this interpretation happens, then the eBPF converts itself to the assembly language code, and then it gets injected into your kernel space and then runs as an event trigger. That's it. So that's the whole philosophy of how verifier works, how loader works for eBPFs. So at the end of the day, you see there are two things which kernel try to ensure. One is the safety, and other one is the performance. So the performance, as I said, is not affected at all. So if you have a production workload running Kubernetes cluster, the memory, let's say, is 1 GB for that particular pod. If you run that eBPF as a sidecar implementation or a daemon set implementation, forget about it. Or even if at the kernel level where the cluster is running, I'm betting you that the latency of that particular application is not affected at all. Even if it is affected, it's like for microseconds or something. So that's what gives an added advantage to eBPF other than the traditional cloud security solutions that we have. So now let's come back to the hello world of eBPFs. So here, if you see, so eBPF programs are written in C. Okay, C programs are then translated to assembly language, and the assembly language execution happens. But eBPFs program can be written in high-level languages as well. But the crux is that even if you use some sort of code compilers, you have to write your program in C. So for example, if you see this particular code, the code is written in Python, but the eBPF module is written in C itself. So the program section, which is this one, is actually inside the eBPF, the one is actually C. So let's fragment this out and let's try to understand what this code does. So the first part is to do the import BCC from BPFs. So this is nothing but a Berkeley Packet Filter code compiler, so compiler collection. Okay, so this is responsible for compiling your C program that you have written over there into assembly language, but at the Python's level. I'll talk about it when I do the fragmentation goes further. It's an open source project. You can check it out. So they have extensions for Python and all the high-level languages that they have. Maybe I think Golang as well. So the next one is actually our eBPF program, which does nothing. If you see, it's actually printing. So BPF trace print is, think of it as a printf, cout, or println, or print function of BPFs. So it's doing nothing. If you see, it's whenever the function hello is executing at the kernel level, it'll just print hello world. That's it. But when this execution will happen, it's based on the events. So we'll have to register those events inside kernel, but via user space. So let's see how it is done. It's done in the next section. So no, not in the next section, but in this section, we perform the compilation. So the BCC compiler, like the BPF that we have imported from the BCC, is performing the compilation. So at this level, your code is compiled by Python. So usually you compile your code from console, but now Python is compiling your code. So this code is now compiled and is converted to an object notation, but inside memory. And the next thing is, now we have to attach this eBPF program or the object that we have to some system call interface, as I talked about, right? So BPF usually attach the event on a system call interface or anywhere, but I'm attaching it as a system call interface. So what I'm trying to do is, from Python itself, I'm using this object program module and finding a system call with the name of execve. We know what this system call does, right? Let's create a new process altogether and then returns the output of that particular process. So we are taking this system call and we are attaching our BPF program into this system call. So if you see here, we are specifying the name of that particular function which we want to execute, basically the hook of the event. So the event name is system call. The system call says that any function or any event that happens on execve is hooked to hello world. Hello, sorry. And what hello does is hello is just printing hello world. That's it. So that's the fragmentation of this. And then we are just registering the print track trace so that we can see what BPF programs are printing. And yeah, we'll see this execution also happening. So at times, for example, writing a specific use case. For example, let's say you want to do a specific use case of file integrity monitoring of a specific file. Then you'll have to understand what all system calls are being used or not. So we know that we have strace to identify this, and we have ltrace to identify this at the user level. So strace and ltrace, these kernel level functionalities can help, kernel level command line tools can help you understand what all system calls that you can intercept or you can use when you want to do a specific use case. So I have a small demonstration of like how this eBPF is going to work. So I have I'm sorry. Yeah. So I'm compiling the code. The code should run now. Yeah, so the code is running. And if you see, when I'm running this cat command on the right side of the functionality, then I've got the output on the left side, which says that hello world. So whenever you are running a command on the command line, it will create a execve function call, because we know that in Linux, whenever you run anything on the bash, it spawns a new process and runs that command inside the new process. So that's what it is happening. And so yeah. Now what I'm doing next is I'm just trying to see if I do strace cat, what will happen. Now we know that strace is a new, it's a different functionality altogether. So strace will create a new process, and inside that process we have a cat command. So there should be 2 executions of our kernel space should be happening. So if you see on the left hand side, we have 2 executions of our BPF filters. Okay, so yeah. Now I'm just showing that we have execve call in somewhere inside the strace output. Yeah, so we have it. Cool. So now let's talk about cloud security. I don't know why this is not visible. Excuse me. Okay, it's visible now. So I want to talk about few use cases of BPF filter in cloud security. But before I would like to highlight few cloud security needs that we have today So first is the cloud network security, microservice visibility, where actually lot of really good solutions are coming around, where they are integrating packet filtering with AI modules on runtime, and then they are giving you visibility around what all interaction which is happening on the microservices side. So I'll talk about it in the next section. Then we have container security. Right now, in the current cloud security environment, we don't run application inside EC2. I mean, if you are running it, then you are living in, I would say, decade-old age. Right now what we do is we set up our own clusters because of scalability, maintainability, and a lot of other factors. So we have clusters where we run our application as any runtime, like any, let's say, Kubernetes runtime or Docker runtime and all those sort of things. So when our application is running as inside a container, then the visibility that we have or the access that we have for the application is very much limited. So the cloud security is another challenge itself. And then on top of it, we are having our infrastructure as Kubernetes. So the level of visibility that we have for the application is again getting reduced. So with eBPFs, you can actually get good visibility as well as the control on the applications which are running inside your pods. The next one is DOS mitigation. So if you know, DDoS mitigation is actually a challenging task, but eBPF, there is a lot of research going on how you can mitigate, or you can at least do some sort of mitigation attempts on DDoS when it comes to the applications. And the last one is data protection. So we know that whenever the companies are attacked or the intent of attacker, they have very limited attempts, like limited ideas that they should either send some ransomware attacks, or they should either do the exfiltration of the data that company holds, because that makes money for attackers, right? So data protection is a really, really important aspect of cloud security. And I'm telling you, we can actually leverage eBPF and to do a lot of things around data protection. So this is something that I'm actually working on right now. Maybe in the next conference, you will see a solution open source one, which would be around data protection, also on eBPFs. Now let's talk about one of the example use cases that I have written to show that how eBPF can do, I would say, network level real-time identification and block. So eBPF can be used to monitor network traffic in real time, we know, because that's how they actually came into existence. That was their first application that came into existence. But on top of this, they can do suspicious activity identification, data exfiltration, DDoS attacks, migration, and all those things. So I have another code that I would like to show. Yeah. The example is to block HTTP traffic. Is it visible at the back? Cool. All right, let's just increase the font. The code, again, is very simple. You have a program written in C as one of the Python objects, and it does the following thing. So what it does is it inspects, so you create a function that inspects an XDP module. So what XDP is it's express data paths. So if I have to put it in a simple way, think of it as, for example, any packet that is flowing on the network, kernel gives you extensibility to access that packet via XDP. So you have interface, you link your eBPF module to that interface via XDP paths. So you write right now we are writing a function which can do this XDP identification. And now I have some sort of fancy logic written here. So if you go back to your networks class, computer networks class, you know that there is at any interface level, there is the organization of packet, right? You have a data, then you have data layer, then you have network layer, then you have transport layer, then application layer, if I'm not wrong. So there is an organization of it, and your network level traffic is at some, or the TCP level traffic is at some location. So this code is doing that only. It's trying to identify what destination port the packet is being going to, because the code wants to block the HTTP request. That's what we want to do with the eBPF. So I'm just doing that. And after getting the destination port, I'm trying to see if the destination port is 80. If the destination port is 80, just print a message that blocking outgoing HTTP traffic to port 80. And then there is a return of XDP drop. So basically drop that packet. Okay? So in the previous example, we just saw the monitoring side of eBPF, but now we are seeing the, I would say, the control part of eBPF, where eBPF can just also control your, I would say, the interaction or the events that are flowing in between. If that is not the case, just simply pass it. And that's the same thing. We are compiling our program, but this time we are compiling with some sort of additional flags. That's okay, nothing fancy. And then we have, in Linux, we have multiple interfaces. So the virtual machine where I was running this code had two interfaces, ETH0, ETH1. So I'm actually linking this XDP or the eBPF to both the interfaces. Again, nothing fancy. loading this inspect function, attaching it to the interface. I know this can sound really intimidating, but a lot of library documentation is available outside, so you don't have to be worried about it. Even if you are worried, you can ask ChatGPT. It's the best source of documentation for me now. And yeah, so I'm just running that program, and let's see how it works. So execution should start. The Python program should, yeah. So the eBPF is attached to both the interfaces. Now, when you try to make a curl request to HTTP destination port, I'm using example.com, you will see that block is actually happening in the real time. Again, I'm saying it's not fancy, but I'm just trying to give you the essence of how eBPF can actually control and take the control of the things as well. But if you do it on HTTPS port, the request would pass as it is. Nothing is going to stop. And this is happening at the kernel level without affecting the latency of the call. So the network call, let's say, takes 1 second. Now also it is taking 1 second, 1.000 seconds, 0001 seconds. So yeah. The next I want to talk about is microservices visibility. If you have ever worked with for example, if you work with a startup, when the founders create their first product, what they do is they write everything as a monolith. That's the very usual story with all the startups that we have. But we all know that from design or engineering perspective, microservice approach is always good. But there are additional cons associated with the microservices. The good con that I can think of is, for example, let's say if you have SPI data, you won't want to have the visibility how that SPI data is flowing across the services. For example, SSNs. How that SSN is flowing, because if we go by regulations or GRC compliances, then we have to make sure that to pass the audit, we have to communicate SPI in encrypted form. But working with microservice architecture, we are not even sure of it unless you go to the code and see. So microservice visibility is a really important part of cloud security, and trust me or not, eBPF can help handle that situation very well. I've not considered a demonstration around it because there are a lot of solutions out there in market. If you just search for eBPF visibility solutions which can do microservice visibility, you'll find a lot of them, like really a lot of them. There are also open source extensions which are there. So I've skipped this part, just highlighted it here. The next one is data protection. I've already talked about it. And let's see how it works. So what I'm doing is, I've written a very small code with good comments. And that code, what it does is it actually monitors all the accesses which are made by user space application or user space application. So in cloud security, this is also known as file integrity monitoring, where you actually put checks or alerts on what all can access what files. And there are already existing solutions out there in market, like traditional existing solution, which is Tripwire. I'm not able to recall anything, but yeah, anything else. But yeah, Tripwire is one of them. But if you see Tripwire or any other file integrating monitoring solutions which exist, they use a classical approach, which is iNotify based. So in Linux, we have kernel probes which are known as iNotify. So they use iNotify for doing file integrating monitoring. Now the problem with iNotify is that, if you've worked with that, you might be aware, but the problem with iNotify is that if you keep on adding the list of directories, or if you can keep on increasing the list of directories, iNotify actually starts to add more latency to alerts. It's not good. So now we know that there are solutions like packet filtering. So can we leverage packet filtering? The answer is yes. So we can use BPFs to do that. And I have a small code as well that I would like to show. Don't get scared of this code. This code is, again, nothing fancy. It's very simple. It's just setting up some flags and then creating an alert, again on Python level itself, to see what all files are getting accessed. You can write your own filters on top of it as an additional filters. For example, let's say in Linux, you have in your infrastructure, you have some secret file which is integrated to Kubernetes. And you want to make sure that what all services are accessing it. If the service list belongs to allow list, then only allow, basically access controls. So you can do that as well. But right now I'm not doing anything that fancy. I'm just having a C program, which I've written specially like separately from Python code, because we have only seen like Python having C, but now I have just segregated that out. And yeah, this is the C program, which actually put event notifier for all the system calls which are used for accessing a file. So yeah. Again, this program just takes that and put it on the open@, system call. If you can see it here, attaching it to the kernel probe. Don't worry, I'll share the snippets of these code with you. And just attaching it to the kernel probe and just monitoring it out. So let's see that in action. Yep. Although I would like to mention that when you run a eBPF program, that takes some time to actually get loaded into memory. So if you see on the left-hand side, when you run your program, the program actually started monitoring. Now, since I was running this as inside a remote setup, you can see a lot of SSHD flags, like SSHD processor accessing a lot of files, right? So yeah. And if you try to access, let's say, etc password file, then also then alert will be created. Let's see, where is that? Yeah, it is here. And you can see that user ID, which is 0, because I was logged in as a root, is trying to access this particular file on SSH terminal. So yeah, that's how you can use eBPFs also for doing file integrity monitoring. Now, extension to this would be to write your own IDS and IPSs or data exfiltration alerts. Let's say if someone is trying to exfil your sensitive information from your cluster. So yeah. This is done. So yeah, these are a few things. Now, if you see I would like to mention the few takeaways from this, that eBPF is an easy B. It's not really fancy. Trust me, it's very easy. You just have to know the library, and you don't have to go to documentation as well. We have ChatGPT for simplifying the documentation, although there could be some issues with it, but eBPF is easy. And the most important thing is it's a non-intrusive way. Although it gets inside the kernel, but it's a non-intrusive way because it doesn't affect anything on your application side. And the last thing is there are no boundaries to eBPF. I would like to leave you with one idea that can you think of a solution that you write which takes eBPF, which takes all the data that you have, put it on, let's say, some sort of classifier on AI side and classify your real-time activity. That is possible, right? It's just a high-level program that you have written. And it also works in real time. So that is also possible with eBPF. So yeah, there are many more applications. There are no boundaries around it. Yeah, so you should definitely check it out. And if you want to learn more about eBPF in detail, so this is a link to GitHub repository. I'll spare you some minutes so that you can take a photo of it if you want. It's a very good repository that talks about how you can use Python for writing your eBPF modules. It starts from scratch. Even I've learned from this repository. So it will be a good one for if you want to really explore things out. Yep. So eBPF and cloud security, that's it. So thank you, Dziękuję bardzo.